So in 7.3, this really starts our last big topic. This starts our last big topic for the school year, really. Okay? Everything we do from here to the end, other than the final, of course, is going to involve what we learn today. Okay? What we're learning today, this is starting on how to solve for exponents. We talked about that before. We've had problems where we had to solve for t and all those financial problems, remember? And at that point, we had 3 different sets of those where I said, well, we don't know how to do that, so we just guess and check, right? We plug and chug, we guess and check, we see what number works. And that is a long and tedious process. And it's not very accurate. I mean, because we were able to guess it down to 1 decimal place, but what if I wanted it to 4 decimal places? That's a much longer process, right? So it's not very effective, it's not very good, it's not really how we would do it. Okay? So today starts the process of how do we solve for exponents. I told you guys we would know how to do that by the end of the year. So, to start out with, let's talk about logarithms. Okay? Logarithms. Now, all year long we have dealt with a phrase for graphing and graphing shift. That was x is hexed, y is y's, right? We've done that all year long to help us deal with shift. Well, I'm going to give you another phrase for logarithms today. A log, which log is short for logarithm, a log is an exponent. A log is an exponent. That is the phrase you need to remember. So, our essential understanding here today talks about exponential function y equals b to the x, which we've dealt with the last couple sections. They say it's 1 to 1. Really what that means, we haven't talked about a 1-to-1 function yet. A function, as you know, is where you have 1 input gives you 1 output, right? Well, in a 1-to-1 function, the inverse is also a function. So we have an original function and its inverse is a function, so we call them 1-to-1, meaning that you have 1 input gives you 1 output on both the original function and the inverse. Okay, it's a fancy way of saying 1-to-1, fancy way of saying that both a function and its inverse are both functions. Okay, but what we need to know here is that the exponentials, we have functions. Well, then their inverse are also functions. And the inverses are written like this. The inverse of an exponential function is a logarithmic function. Okay, it's a logarithmic function, a logarithm. Now, the way we read that would be log base b of x. So that would be y equals log base b of x. Okay, that is a logarithm. And please remember, we'll deal with graphing these at a later date. But please remember that a logarithmic function is the inverse of an exponential function. So we're going to go through and we are going to write our logarithmic functions in exponential form and in logarithmic form. Okay? So to do that, we need to know this little translation right here, that little rule. Okay? So it says log base b of x equals y if and only if b to the y power equals x. All right, that's what we're going to use to go back and forth between exponential form and logarithmic form. Now, of course, this one is exponential form because it has things written with exponents. This one, of course, is logarithmic form. How do I know? Because it has log in it, right? It says log in it. So when I'm going through and doing these, for example, let's say I have 2 to the 3rd power, and that equals 8. Okay? That is, of course, written in exponential form because I'm using an exponent. I want to rewrite that in logarithmic form. Okay? So to rewrite that in logarithmic form, I'm going to say, first off, that my phrase that I gave you at the very beginning of the lesson was that a log is the exponent, right? A log is an exponent. Is in math means what? Is means equals. Is means equals. So if I'm writing this in logarithmic form, I'm going to say that my log, leave yourself a little space because we're not done with that yet, but the log is going to equal the exponent. Well, what was the exponent? 3. So the log is the exponent. Okay? Well, now wait a minute. Exponents, we've talked about exponent notation before. The number down below, this number right here, what do we call that number? The base. That's the base of the exponent, right? So that's the base of the exponent. Now if you look back up above where I had you write down what it means or how you read logarithms, I say log base b, right? That phrasing, that base, means the same thing. So if this is the base of the exponent, the base of our logarithm gets written down here. This is log base 2. Okay? And then we only have one thing missing. What's the one thing that's missing here?
8.
The 8. Okay, so remember, log is the exponent, so you're going to know that log equals 3, because 3 is the exponent, and know that the base of a log is the same as the base of the exponent. We use the same language because it's the same thing. So this is log base 2 of 8 equals 3. Now, another way that we can translate this, another way that people do this going from logarithm back to exponential form, is I kind of call it the recycle method, because it kind of reminds people of the recycle symbol. Okay? And all you're doing is starting at the base and saying 2 to the third power equals 8. Okay? 2 to the third power equals 8. That's how you would change that logarithm back to the exponential form. Okay? Okay, well, logarithms are handy because they allow us to solve for exponents. For example, I could have rewritten this as 2 to the x power equals 8. I'm now solving for my exponent, right? And so logarithms allow us to ask the question, if I rewrite this, 2, or log base 2 of 8 equals x. I'm solving for that x variable. I can say 2, or I actually just, let me say, instead of saying multiply, let's say 2 to what power? Two to what power equals 8? That's what we're asking ourselves when we do logarithms. Okay, if I have log base 2 of 8, I want to know 2 to what power equals 8. Okay, so we're now learning how to solve for those exponents rather than doing just guess and check. Okay? Any questions on how to rewrite logarithms from exponential form to logarithmic form? That's the big thing we're doing right now. No. Okay, so then let's take a look at an example here. Let me see here. All right, what is the logarithmic form of each equation? So first things first, what I would do if I were you is I would rewrite this the same way every time to make sure that we get used to seeing it. Okay? Logarithms is one of those things, I'll be quite honest with you, that it baffled me when I first learned them. I was like, man, this is confusing. This is hard stuff. And then all of a sudden, one day, it just clicked. You see the pattern. You're like, why was this so difficult? Okay? So I'm hoping that you guys will see the pattern sooner than I did when I was your age. All right? And the key to doing that is rewriting this first. I don't want it to say 100 equals 10 squared. I want the exponent stuff written first in my equation. So I'm going to rewrite this as 10 squared equals 100. Okay? Because now I'm seeing it the same way every time. All right? And then I remember the phrase, log is the exponent. Right? So this is log is, what's my exponent?
2.
So my logarithm is going to equal 2. Well, what's the base of that exponent? 10. So this is log base 10 of 100. Log base 10 of 100. And what is it saying to me? It is saying 10 to the second power equals 100. 10 to the second power equals 100. That is what this is saying. All right? Questions? Let's try part B here. Again, to see it the same way every time, I'm just going to flip that around. 3 to the 4th power equals 81. Okay? So then my log is going to equal what? Log is the exponent. So my log is going to equal 4. The exponent. The base of my logarithm is going to be 3. And so the only number missing is 81. Log base 3 of 81 equals 4. And please pay attention to how you're writing this. Log 81 and 4 should all be on the same line. The base of the logarithm is then a subscript. It's below the main line. Okay, we've got to make sure we write these properly. That way we don't accidentally think that we're taking the log of 381. Okay? All right, so I'd like you guys to take a moment and do A through C. Rewrite those logarithms. All right, let's see how we did. So looking at part A here, again, to stay consistent with how I'm looking at these things, I would flip this around. 6 squared equals 36. And so now I'm going to write log, and what's that going to equal? 2. The log is the exponent. What's the base of the exponent?
6.
So what's the base of my log?
6.
And so log base 6 of what?
36.
36 equals 2. Okay, and again, you can check that using that recycle method. 6 to the second power equals 36. That's exactly what we had. 6 to the second power equals 36. All right, part B. Part B looks confusing because there's fractions involved. But you know what? Set it up the exact same way. All right, I still want to flip things around just because it keeps things looking consistent for me. So therefore, my log is going to equal 3. What's the base of my log? 2/3. And I'm taking log of what? 8/27. So log base 2/3 of 8/27 equals 3. What does that mean? That means 2/3 to the third power equals 8/27. Okay? And our last one here, rewriting that as 3 to the 0 power equals 1. So therefore we have log equals 0. Log base what? 3 of 1. Okay, so, and again, that means 3 to the 0 power equals 1. What is 5 to the 0 power? 1. What is 7 to the 0 power?
1.
What's the square root of 2 to the 0 power?
1.
So, what this is telling us is a rule for exponents. Or a rule for logarithms, excuse me. is that the log base anything of 1 is going to equal 0. Log base anything of 1 is going to equal 0. Why? Because b to the 0 power always equals 1. Remember, b to the 0 power equals 1. So therefore, log base b of 1 will equal 0. Okay? Log base anything of 1 will equal 0. So let's go ahead and start solving logarithms. Now, we're going to learn this without the calculator. Okay? So one thing we can use, though, is a roots chart. You might want a roots chart handy. So if you have your roots chart, dig it out. We want to evaluate log base 8 of 32. So to evaluate this, what we essentially do, log base 8 of 32, we want to find out what does that equal. And so we essentially write a little equation and just say, well, that equals x. We're solving for x. Then what I want to do is I want to rewrite it in exponential form. So 8 to the x power equals 32. Okay, so I'm solving for x. 8 to the x power equals 32. Now, something I want to show you. Now, go back to that first example I gave you guys when I said 2 to the third power equals 8. Can I rewrite 8 using a base, using exponents? What does 8 equal? By the way, it's up on the board already. 2 to the third power. Notice the exponents are the same. And so if I asked you guys 2 to the x power equals 8, what's your answer? 3. Why? Because 2 to the x power equals 2 to the third power. And so therefore, x equals 3. So if you have, in an equation, if you have the same base across the equal sign, if you have the same base across the equal sign, that means the exponents must be equal. Doesn't that kind of make sense? 2 to the x power equals 2 to the third power, therefore x has to equal 3, right? Okay, well we want to use that same principle over here with 8 to the x power. Now, is there any way to write 32 to have a base of 8? Using your roots chart. No, because 8 squared is 64, so that doesn't work for us. So what we're going to have to do then is actually rewrite both 8 and 32. So can I rewrite 8 to have a base raised to a power? 2 to the third power. Okay, so I can say that 8 is 2 to the third power, and then that's raised to the x power. And 32, well, if I have a base of 2 over here, then let's see if I can use a base of 2 for 32. 2 to what power? 2 to the fifth. Okay. So, again, thinking back to Unit 5, rules of exponents, if I have an exponent raised to an exponent, what do I do with those guys? I multiply them. So I have 2 to the 3x power equals 2 to the fifth power. That means that 3x must equal 5. And I ran out of room there, so I'll bring it up here. So if 3x equals 5, to solve for x, I simply divide by 3. X equals 5/3. That's the exponent. We could test that. If you take your calculator and you take, let's see, back to our exponent rule right here. If I bring that over here and say, all right, what's 8 to the, so on the calculator, take 8 raised, parenthesis, 5 divided by 3 power. It gives you 32. It works. Okay. A lot of people's just kind of staring at that real quick. Let's try another one before we get too lost here. This one actually is quite a bit easier. if I want to evaluate log base 5 of 125, first thing I do is I set up a little equation. I just say that equals x. I'm solving for x. Okay? Then I want to rewrite it in exponential form. So this is 5 to the x power equals 125. Now what I want to do is I want to rewrite both sides of my equation to have the same base using exponents. So I already have base 5 to the x. Now can I rewrite 125 to have a base of 5? Yes? No?
Yes.
Yeah, okay, so it's 5 to what power?
3.
5 to the third. So 5 to the x power equals 5 to the third power. Well, therefore, x equals 3. Okay? I told you guys on the test there's going to be 2 parts to the test, just like in the last unit. 1 part with calculator, 1 part without calculator. This stuff we're doing on this side today, this is what I'm expecting you to do without a calculator. Okay? We should be able to do this without a calculator. Let's try another one. Log base 4 of 32. So again, I'm trying to evaluate that. I'm trying to solve that. I'm trying to find out what does that equal. So I set it equal to x. I'm solving for x, right? I need to rewrite that as 4 to the x power equals 32. So what base can I rewrite 4 into? 2. Okay, so it's 2 what? 2 squared raised to the x power. And how about 32? 2 to the 5th. Okay, remember, a power raised to a power, you multiply. So this is 2 to the 2x power equals 2 to the 5th power. That means that 2x must equal 5. And so x equals 5 halves. So looking here at part C again, I want to set that equal to x. I'm solving that logarithm or evaluating that logarithm. So in rewriting this, 64 to the x power equals 1/32. I want to do this in parts. I want to deal with the left side first. So can I rewrite 64 using a different base?
Yeah.
4 to the third? Okay, then can I use 4 and rewrite 32 using 4 as a base? No, I have to be able to use 64 and 32 in the same base. 2 again, right? 2 to what power gives me 64?
6.
To the 6th power. 2 to the 6th power is 64. And so that means I have 2 to the 6x power. All right, well now I got to deal with 1/32. I want it to be a whole number raised to an exponent. So the first thing I want to do is take that 32 out of the denominator of that fraction. So that's going to be 32 raised to what power?
To the x.
-1. 32 to the -1 power. Brings it out of that denominator. So now I need to rewrite 32 to have a base of 2. So 2 to the 5th power, I heard someone say, that's raised to the -1st power. So therefore, I have 2 to the 6x power equals 2 to the -5th power. Now I can say that 6x equals -5. And so therefore, x equals -5/6.